So, good morning, everybody. I will continue on the chapter about mortality. And I was talking about life tables here with you in the previous class. So I pretty much showed the example of this life table for the US in 2010. And I explain each one of the columns here, the probability of dying, the number of people surviving to the beginning of each one of these age groups, the number of people dying within the age group, the number of person years that people live within this age group, and then the TX column, adding the column from the big LXN cumulatively from the top to the bottom. So this one here adding all these cells, this one here adding all these cells, and so on. And then when we get this total number of person years lived by a specific age group until older ages and divided by the population that was alive at the beginning of that age group, we have life expectancy at birth, right? So I went in detail with you in the previous class, explaining each one of these terms in the life table. And then we stopped here in this graph that pretty much just shows the typical shapes of the life table functions. So the probability of dying in each one of the age groups, it starts high. That's pretty much the probability of dying before babies reach age 1. And once babies reach age 1, the chances of dying decline a lot. So it declines, remains low, but increasing as people get older. And then when you get in older ages, the chances of dying, the probability of dying increases a lot. As probabilities of dying increase a lot, what happens is that the number of people who survive until the beginning of each age group starts to decline. In that previous life table, the little L0, the radix of the life table, the number of people that we are making that will be born in the life table, equals 100,000. In this graph here, it's 1. So in some life tables or some representations like this, the little L0 can be represented as 1, 100, 1,000, 100,000. So this one here is pretty much saying that we have everybody alive at the beginning of that, at age 0. So that's pretty much the number of people born in that specific year that will be exposed to the probabilities of dying. And as these people start to die because of this, the number of people that will survive until the beginning of the next age group starts to decline until everybody dies. So this probability of dying by age group is make people die, and then people will not survive to the beginning of the next age group. And the number of people dying in each age group is symbolized here by the DX5 or the DXN. And the number of people dying is really high before reaching age 1, exactly because of the rate, the probability of dying is really high. And then the number of people dying is high. It declines as these guys here. And then it starts to increase as this one. And then this one keeps increasing, but you see that the overall number of people dying increase until a certain point, but then it declines. It's just because you don't have as many people alive anymore at that point. At that point, you already have people have died before here. So you don't have as many people alive at that point. So even with really high probabilities of dying, the number of people dying by age group declines. And the life expectancy for each age group, what we see is usually because the infant mortality rate is high, the life expectancy at birth, at age 0, is smaller a little bit than the life expectancy in the next age group. And then the life expectancy in each one of the other age groups starts to decline. But remember, if I want to know if someone reached the age of 30, how many years on average that person is expected to live beyond age 30? That's this number here, right? If someone survive up to age 30, this person is expected to live an additional, let's say, around 40 years. So how many years on average that person will live? 40 plus 30, 70. Okay, so that's how we read this. And I will show you the life table in Excel. It's going to be the next step. But just before that, I will just go back into some discussion that we had about stable population. Life tables, the one that we use to calculate life expectancy for each age groups, is really important. It was really important for the development of the stable population theory. Basically, analyzing the life tables, what this theory mentions is that if a population is kept close, let's imagine that we don't have immigration or emigration in that country. So there are no people coming in that country from other countries, and from this country, nobody is getting out, right? So there is no migration. If you're talking about the country, if you have a life table about the state, let's say that there is no internal or international migration, nobody coming in or going out from that state. Whenever we start to do this theoretical analysis in demography, in which we say, okay, let's consider fertility and mortality, but let's say that there is no migration. Whenever we do an analysis in demography that we are saying, oh, let's not consider migration, the effect of migration, that analysis is using the assumption of a closed population, right? The population is close to migration. And that's exactly what the life table is, right? The life table has information about mortality and fertility, but it does not have information about migration. Where is the information about mortality on the life table here? The information about mortality is exactly column 2, the probability of people dying in each one of the age groups. Where is the information about fertility? Fertility is the little L0, 100,000. The overall number of people who will be born and will experience these chances of dying. These people here experience this chance of dying before reach age 1, this amount die. This minus this, we get this amount of people left. These ones are exposed to this chance of dying. This number of people die. This minus this goes there. So mortality is here, fertility is there. But we do not have migration. But what demographers came up with that stable population theory is that, let's say that these chances of dying here are not going to change as much anymore. The probabilities of dying are not changed as much anymore because we already improved so much mortality. Mortality declines so much that it's not going to improve as much, and it's not going to vary so much by age group. And let's consider that the overall number of people dying in that country or in that population will not change much. It's going to be always around the same number, right? If that happens, that population will have a constant age distribution. It's going to have pretty much the same proportion of people by age groups if these probabilities of dying and the overall number of people being born do not change for several years, for several decades. If these mortality rates, they kept constant and the overall level of people, the overall number of people being born, it's similar over several decades, you're going to have a constant age distribution. How do you get that from the life table? You pretty much get it from column 5. If you get this column here and represent it in percentage terms, you can create pretty much a graph with the age sex structure of the population. So you have to have the life table for men, the life table for women, and you get this number here and divide by the total of this column to get the percentage of people here. Because this column, what does it represent? The overall number of years that these people here lived in this age group. It's here. The overall number of years that these people here lived in this age group, 397,000. The overall number of years that these 99,000 live in this age group, 496, and so on. So this number here, if we represent it in percentage terms, we can get the pyramid, right? And we have to get this information by sex. And just remember, what's the total of this column? Can you add it right now in your head and just give me the number? It's hard, right? So just reading the slide, 7,866,027. That's what I said at the beginning of the class, right? This number here, it's adding everybody. So what we pretty much get, we get this number divided by this number divided by this number divided by this. We have the proportional distribution of this population using this stable population theory with the assumption that age-specific mortality rates and then age-specific mortality probabilities don't change much over time, and the overall fertility, okay? So that's pretty much what the stable population theory is telling us. If a population that's close to migration experiences constant schedules of age-specific fertility and mortality rates, it will develop a constant age distribution. Where do I get that from? From the big LXN column. It will grow at a constant rate irrespective of its initial age distribution. If there are more if there are more people being born overall than people dying, you have a constant increase. More people dying than being born, you have a constant decline of the population. Similar numbers of people being born and dying, you have a population that's not changing in size, okay? So that's pretty much saying the same thing, the stable population theory. These slides here, I pretty much got the same slides from the lecture 1, from the beginning of the semester, of this course. So just to make it clear that discussion that we had at the beginning of the semester ties into the life table. So the stable population theory considers a closed population, a population in which migration does not happen, so we are not taking into account the effect of migration. If a population experiences constant age-specific fertility and mortality rates for a long time, it develops a constant age distribution and grows at a constant rate, irrespective of its initial distribution. Same thing as the previous slide. Demographers sometimes indicate that stable populations forget their past. The age distribution for stable population depends on the underlying age-specific mortality rates and the rate of growth. The rate of growth is pretty much saying if we have more births than deaths, increase in size of population over time. More deaths than births, decline in population. Same number of births and deaths, population doesn't change in size. But the distribution in these 3 scenarios, the distribution of the population is similar. I said 3 scenarios, right? Births higher than deaths, deaths higher than births, and then the situation in which you can have the similar amount of births and deaths. In this specific case in which the number of births and deaths is equal in a specific population, in a specific year, it's a kind of stable population where you don't have growth and you don't have decline in the size of the population. That specific case of stable population is called stationary population. So the stationary population is a stable population in which the birth rate equals the death rate. This results in no change in the size of the population. It also is doing the analysis considering the population closed. In other words, we are not taking into account migration. And then I showed you this debate that the demography community had on Twitter early this year in January, because of this tweet, a series of tweets actually posted by Elon Musk. He kind of like was criticizing the United Nations projections and just saying, oh, an easier way and quick way to kind of project the population to the future is just multiply the last year's births by the life expectancy. I think this life expectancy that he's talking is the life expectancy at birth. And his point is that since fertility is declining, given downward trend in birth rate, that is best case unless reversed. So we expect that population size will decline because fertility is declining. So he put it out there. He never took a class like this, of course, but he's a billionaire, so they can say whatever they want, right? That's how our societies work nowadays, but we know better than that. And demography is not just multiplying one number by the other. To do projections of the population, to know how the size and the distribution of the population is going to be in the future, we need a much more detailed analysis than what he suggested here. So that's not how we do population projections in demography. It's not just by multiplying the overall number of births by the life expectancy at birth. And that's exactly the discussion related to stationary population. So Ilya Kashnitsky, an assistant professor from the University of Southern Denmark, he kind of like made some quick exercises to show how baseless was that information. And for you guys, it's important to know that is to understand how the knowledge that we are learning here in this course can help see how important the projections that the United Nations are doing, how difficult they are, and what is behind them. So his point here, maybe this is a bit overkill, but let's illustrate how this projection method of Elon Musk, actually a stationary population assumption, worked with past data using the human mortality database. And I showed you in previous classes the website of the human mortality database. So Ilya Kashnitsky, he got the data, like real data of mortality from several countries. And in this example here, in this graph, he has the case of the US. And what he is pretty much, the point here is that if you just get the overall number of births and multiply by the life expectancy at birth, you are assuming a stationary population, right? So what Elon Musk suggested was pretty much making projections using the stationary population assumption. Why is that not appropriate? Why is not so easy just multiplying the last year births by life expectancy? Because the age-specific mortality rates, they have not been constant over time. Right? Fertility has not been constant. I mean, you could still get the fertility level doing that assumption, but the mortality is not constant. So by doing the exercise that he said, you would be actually overestimating the size of the US population instead of using actual data of mortality that was measured since, I guess here was like around 1940s, right? Until 2010, around that. So if we use, so the stationary population theory is really important to give us an idea of how the size and the distribution of the population is going to be if you have constant mortality and fertility. But that's not what we have. If we use that, in the case of the US, we would be overestimating the size of the population instead of getting this actual data on the size of the population. And this size of the population here in millions, right? If there is just one take-home message from this thread, life expectancy is a snapshot of the current mortality. It is not a projection, forecast of the actual experience of the newborn cohorts. Mortality is still changing. I mean, the pandemic now is making for mortality go up again. I already showed it to you guys here. Already estimated showing that between 2020 and 2021, life expectancy in the US dropped 1.5 to 2 years because of the pandemic. So mortality is still fluctuating. And the life expectancy is based on period data, cross-sectional data. It's how mortality is right now, right? So we cannot make these projections assuming that mortality is going to be constant, but it's not. Still, stationary population theory, the stable population theory, is important because it gives us an idea of how the population is going to be. But since mortality is changing, we have to update this data every year. And this researcher from the Max Planck Institute in Rostock, Germany, Jonas Scholle. It's true if we look at world population, no migration, and it's stationary. In other words, birth rates and death rates have been equal for several generations, and mortality remains constant, whereas fertility is allowed to decline. Mortality remains constant because we are taking life expectancy at birth. Fertility is allowed to decline because that's what he's mentioned here on his tweet. Then we reach the peak population, which can be estimated by the number of births times the life expectancy at birth. But of course, these assumptions are not strong. These assumptions are not good because that's not what we had, right? We are not doing this kind of analysis here. If we try to do it for each individual state, we will have migration. Migration is zero only if we are doing the analysis for the whole world. And the number of births and deaths have not been equal for several generations. And the age-specific mortality rates has not been constant. Okay, fertility might be declining, but all these other assumptions here are not true from what we are experiencing. So population projections cannot be done in such an easy way, okay? And these are just other examples. Kashnitsky, he did the same exercise for other countries, but instead of just showing the population size in millions here, he just compared this number here to this number here, divided this one by this one to see if it was higher or lower than the actual one. So this is the estimate based on this Elon Musk theory or the stationary theory, population theory. If it's above 100%, that's the stationary population theory is overestimating the size of the population in that year. If it's below 100%, it's underestimating the size of the population for that specific year. If you download this slide, you can read the names of the countries here. Here are just some examples for Taiwan, Russia, and the US to show that if we simply apply the stable population theory or the stationary assumptions to project the population, we will not get good estimations. They will be either overestimating or underestimating the actual population. Because these countries have migration, these countries have different birth rates and death rates. They have not been equal for several generations. Age-specific mortality rates have not been constant for several generations. That's why this is not a good exercise to do. It gives us an idea, but we would have to control for migration, and we have to update the data every year in order to see fluctuations of birth, death rates, and age-specific mortality rates, okay? But that's interesting, right? Like a 3-sentence, it was actually a thread, but like this 3-sentence tweet here can generate a lot of like debate in terms of demographic methods And that's the crazy thing about nowadays, right? People in powerful positions say whatever they want without based on knowledge and facts. And I'm sure that more people read and liked this tweet than this really well done analysis of how this is baseless. Completely nonsense what Elon Musk wrote, okay? Cool. So now and these extra slides here on Life Table, they just cover the same things that we discussed before, so we will not go on them in detail. It's just pretty much similar notations, but from another textbook. If you want to read it, it might make it easier for you to understand it. And then I will show you now the life tables. And here, if you go in the course website, in the portion here about mortality, you can download the example of life table in Excel. When you download, is that compressed file, so you uncompress it, becomes in Excel. It's pretty much one Excel file here. And the raw data that I got, it gives us the number of people dying in each one of these specific age groups for women, and the same thing for men, right? So we just have this raw data that I got, and from was exactly from the CDC that I got all this information. The data in deaths is more detailed in terms of age group. It goes until 100 plus, but the population in this case here just goes until 80 plus. So the life tables that I will be doing here now, the last age group will be 80 plus because of the data availability, okay? And we have that from 0 to 1, so we can calculate mortality rate, 1 to 4, and then until 80 plus. And for 80 plus, I will add these last deaths here from 80 to 100 plus, both for men and for women. So I will just, based on this information here, from this table, I organize it. So now I have, this information is for mortality in the US in 2017, right there. And we have the information for females, males, number of deaths and population. And here is just getting information from the raw data spreadsheet. So this one is H2. It's going to be this one here. And then the other one will be I2 is this one here, right? And the last one is adding from 19 to 23. It's adding from 19 to 23 here, these cells, okay? So this is the organized data. What is this data exactly again? The number of people who died in each one of these age groups in the US in 2017 by sex. So we have number of women who died by age group and number of men who died by age group. And the overall population in the country in that year, and this population here, they estimate for the mean of the period, which can be used as an approximation of person years in the denominator of our formulas. So based on this data here, I can calculate a life table for women. And based on this data here, I can calculate a life table for men. This column here is just the width of the interval. How many years I have in this one here, 1 year, age 0, here 4 years, we have age 1, 2, 3, 4, and 5 years for the others until the last one that we have an open-ended interval, right? So getting this data for women, we can do the life table for women here. So let me just zoom in a little bit more. So we have the age group, right? Here, this column, I just add the age at the beginning of this interval. So for the first one is 0, 1 to 4, the first age is 1, 5 to 9 is 5, 10 to 14 is 10, and so on. This column here, we're going to use at the end of the life table. The width of the interval, the first one is 1 age only, age 0, 4, and 5, which is the same as the previous tab here, the organized data tab. Also from the previous one, we have number of deaths. So this comes from the organized data tab, right? Number of deaths until 80 plus. So this is all data that we are inputting here based on observed data. Population, also from there, okay? And then it comes the calculations, right? So a simple one, the age-specific death rates, the MXN. That example of life table that we saw in the textbook, the one that's available in the textbook, already it starts with the QXN, the probability of dying. It doesn't show the rate of dying. This is only the mortality probability, not the mortality rate. The mortality rate, we do it beforehand. How do you calculate the mortality rate by age group? I simply get the number of people who die in that age group divided by population that age group. That's the MXN. So F4 divided by E4. And then I do that for all the cells here, okay? And then I have to see what's the probability of dying. Here we have to use a special formula to calculate the mortality probability based on the mortality rate. The mortality rate, the denominator of the formula, the population, the KXN, the size of the population by age group, is the population in the middle of the period, which is a way to approximate the measurement of person years. So the rate, the denominator, is the population in the middle of the period. The probability, the denominator, is the population at the beginning of the period. The population at age 0, at age 1, at age 5, at age 10. So we have to make this transformation from here to here, right? And that's something that we discussed in the previous class, because what we want to know is like people reaching the beginning of this age group, what's their chance of dying? So we have to change the denominator from this to this, okay? How do we do that? We use this formula here. So the formula for MXN is number of people dying divided by the population in the middle of the period. The time T here is 1 because we're just using 1 year. And there are several different ways, several different formulas to transform the mortality rate into mortality probability. This one is one way to do it. And I'm using this textbook here, Essential Demographic Methods from Wachter. So what do? We multiply the mortality rate by the width of the age group, divide by 1, plus the width of the age group, minus the average years that people lived in that interval, and multiply by MXN. And this column here is a new column from us that I did not discuss in the previous class. The average years in the interval. See, for these cells here, they're really easy, right? If we think that mortality is constant within the 5-year age groups, from 5 to 9, 10 to 14, all these age groups here have a width equals to 5. And if we think, we have the assumption, that's usually the assumption used by demographers, that people who die in this period here, how many years on average they would live? If we think that mortality is constant within each one of these age groups, if I die between the ages of 5 to 9, the chances of dying at age 5, 6, 7, 8, 9 is the same. So I will live on average 2.5 years, right? So what is this 2.5? is pretty much this number divided by 2, right? So it's pretty much getting this number here. This formula here is applied to all these guys. But there are some specificities here. For babies who die before reaching age 1, their chances of dying is much closer to age 0 than to age 1. So it's not just dividing 1 by 2. I cannot just divide 1, which is my n, by 2, which would give 0.5, because I would say that the chance of babies dying at month 1, 2, 3, 4, 5, until 12 is the same. But we know that's not, because babies that die before reaching age 1, they usually die closer to age 0 than to age 1. So instead of 0.5, this number is going to be smaller than that. How do I calculate that? I calculate that using this formula here. 0.07 plus 1.7 multiplied by the infant mortality rate. What is the infant mortality rate? Is the chance of dying, is my capital M, from ages 0 to 1. Where is this number here? It's right here. So how do I implement this formula? That's what I do here. 0.07 plus 1.7 times the mortality rate from 0 to 1. So it's calculated there. Also, children who die between the ages of 1 and 4, those who die between the ages of 1 and 4, they will die closer to age 1 than to age 4. So I cannot simply get number 4 here and divide by 2 and get 2, because it's more likely for children who die between these ages to die closer to 1 than to 4. And the standard is to use the average years in the interval, the A14 for this specific age group equals to 1.5. Right? That's a usual convention there. For the first one, A01, we get information on mortality rate, but this one we don't. It's easier. And for the last one, how do we know how many years on average people will live in this last age group? And it's an open-ended interval. It's 80 plus in our case. So we also use information on the mortality rate of the last group. So we pretty much just do 1 divided by 0.2084. Just divide 1 by this cell here. And this exercise kind of forces everybody to die in that last age group, okay? So in this case here, 4.8. So now we have all the information to calculate the probability of dying in a specific age group. So this formula here is this one. So let's see the numerator. The N, C4 is N. The mortality rate, G4, is exactly the G4 here. Divided by 1 plus the N, C4, the average years in the interval, minus that is D4, is right here, times the mortality rate, which is G4. So we calculate that for everybody, the same formula for everybody. So it's pretty much using that information. It's pretty much using the width of the interval, the mortality rate, and the average years in the interval. Until the last one, that we pretty much force everybody to die. So here, there's no formula. The last one is just everybody dies. 1, everybody dies here at the end. Now we can do the same exercise that we saw in the textbook. We apply the radix for this life table. So how many people will be born and will be subject to these probabilities of dying? 100,000. And we get 100,000 times this, we get the number of people dying. So the number of people dying is pretty much the probability of dying multiplied by the number of people who survived to the beginning of that age group. Since the little lx is the number of people alive at the beginning of the interval, that's exactly what I have there at the top of the table, then that's why I had to have the probability of dying. The denominator is the population at the beginning of the interval. So this number times this number equals the number of people dying in the interval. So that's this formula here. D equal dxn equals qxn times lx. So that's what we are doing for everybody. But after we do this first one, we have to come here to the little l in L1 for the age group 1 to 4 and calculate it. How can we calculate it? We can get 1 minus the probability of dying. 1 minus the probability of dying is the probability of surviving times 1.4. Oh, but this formula here is too complicated. 1 minus the probability of dying times the probability of surviving to the previous age group. A simpler way, as we talked before, is just to get this number here minus this is what will survive to the next one. And that's this formula here. So we can use either formula, this one or this one. So if I apply this one here, it's going to give the same result, equals this one minus this. What am I doing? Number of people who survive, who are alive at age 0. How many died before reach age 1? 510. How many do I have left? 99,490. See, it's the same result. So if instead of using this first formula here, if I use the second formula, I will get the same 99,406. This number minus this number, 99,406. Okay? So I'm pretty much just implementing these formulas, and the death, I just multiply the probability of dying by the number of people surviving to the beginning of the age group until the last one in which everybody dies. 65,000 people die. And then it comes the number of years leave the interval. So we talked about that before. Let me just make this one here a little bigger. So if nobody died in this first age group, all these 100,000 people reached age 1, then number of years lived in this interval will be 100,000. And then we would have 100,000 reaching this next age group. And if this 100,000 reach the next age group, here we would have 400,000, right? So that's pretty much saying that we have 0 mortality here for everybody. And so if you have 0 mortality, what happens? These 100,000 people will survive, will survive, will survive, will survive. So there is no mortality. Then we have an overall, all these 100,000 people lived together 100,000 years in this age group with 1 age, width equals to 1. In the next one, which the width equals to 4, 400,000. And then in the other ones, 500,000, because everybody lived, in this case here, ages 5, 6, 7, 8, and 9. But that's not the reality. The reality is that we have mortality. When we have mortality, the number of years lived in interval will vary. How do we calculate that? We have to say the people who survive to the next age group here, this 99,490, they all lived together 99,490 years in the first age group, right? Because all of them survive to the next one. So we pretty much get this number here from the next one, multiplied by the width of this interval. So when we are doing this formula here, we get, see, the n is C4 times Lx plus n. We are pretty much saying that all these people here survived to the next age group, so they all lived 1 year. What about the people who died in this age group, the 510? How many years on average did they live? 0.1. So the AXN gives us the average years that people lived out of those who died in that interval, right? We are giving a huge discount here, multiplying them by 0.1. And then we get the big LXN. Let's just get one here. It's the same formula applied here. So for example, for this LXN for the age group of 20 to 24, 98,894 people survived to the age group of 25 to 29. How many years they did all live in the previous age group? Since all of them survived to the next one, they all lived 5 years in the previous age group. So it's 5 multiplied by 98,894. So that's the N, C9, multiplied by those that survived to the next age group. Plus, for those who died, the DXN is the J9. Those who died, how many years on average they lived? We have this assumption that people in that age group from 2024, those who died, have the same chance of dying within that age group, 2.5 years. And that's the number here, okay? For the last age group, I have to apply a different formula because, of course, I don't have the next age group because that's the last one. And there are several formulas to calculate the big LXN, and one of them is to get the average years in the interval, the AXN, which is the 4.8, so the D21 here is the A, and multiply by the number of people who died in that interval, because since everybody dies in that interval, there's 65,000 people, how many years on average will they live? That's pretty much the previous formula here without this first term, because we don't have the next age group. Since we don't have the next age group, this term crosses out, is away. So it just remains AXN multiplied by DXN. It's exactly this one here, right? So the formulas for QXN and the big LXN are the more complicated ones to have, to estimate. And then the rest is really straightforward, right? The TX is the cumulative number of years lived from now until the future. So here, just add all these people here until here, the number of person years lived throughout all these age groups. This goes from 1 plus, this one from 5 plus, this one from age 10 plus, and so on, until the last one that's only the last one. And life expectancy at birth, what we said, I told you guys before, like if I want to know the average age of you guys here, 3, 6, 9, 10 people, I add all your ages. What are your ages? The overall number of years that you live throughout your lives. And the years that you lived is similar to the same years that the other people lived. 2021, 2020, 2019, 2018, and so on. I get all your ages, which is pretty much the person years, add them all, and divide by the number of people, 10. Where's that information about all the years lived together? Is the T0, the big T0. was the overall number of people who were exposed here in this life table? 100,000. So I just get this number and divide by this number, I get the life expectancy at birth. And remember, in the life table from the textbook, we finished there in the life expectancy at birth. I will add another one. So for this case here, the life expectancy at birth is 77.9. And then it drops to 77.3. Oh, look at this. Those typical curves that we saw for life expectancy here. In this typical curve, it was low, increase, and then decline. In the case of the US 2017, it's already declining, 77.9 to 77.3. That happens because the infant mortality rate is not so high. So the life expectancy is always declining. But we could see an increase if this the mortality rate was too high. Let me just see, let's put 0.05. See, if I put a really, really high infant mortality rate, the life expectancy at birth is lower here and then go up and then go down, which is exactly what we saw here. Go up and then go down, up and down. But that's not what we have in the US. Mortality rate is really low, so this number here always goes down. And what does it mean, the life expectancy for the other age groups? So for example, here for the age group of 20 to 24. For 20 to 24, we have a life expectancy in that, so that's the E20, right? So the notation here is the E20. It doesn't have the N because we are talking about people entering that interval, E20. For people who reached age 20, they had the chance to die before, but they did not die. They had the chance of dying here, 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 and here, but they did not die. They survive at least to age 20. If they survive at least to age 20, they overcame all of those risks to die, so their remaining years of life will make their average age of death being higher than those that died before, right? So let's just get, how do I understand this? This 58.5, it means that for people who reached age 20, considering this data here, they will live on average an additional 58.5 years. That means that they will live overall 78.5 years on average. How did I get the 78.5? I just got the life expectancy and I added to the age at the beginning of that interval. So I said that this column here we would use at the end, right? So for people who reach age 20, they did not die here before, so they get some bonus years of life. In this case, instead of living on average 77.9 years, they will live 78.5. The same thing for the other age groups. If, for example, for people who reach age 60, they overcame all these different chances of dying. So for those who reach age 60, they're expected to live an additional 21.2 years. In other words, they will live 60 plus 21.2 years on average. They will live on average 81.2 years, conditional on the fact that they survive up to age 60. 81.2 years is higher than 77.9. Okay? And this last column here, I'm just checking if I did the calculations correctly. I'm just dividing this number of people dying by the big LXN. Remember, the big LXN is the number of years that people live in that age group. So that's the real person years that demographers use, right? And this number here, if you compare, is the same one as this one. And this one is based on the raw data, and this one I've just calculated to see if they are similar. So we do the same life table for men, and then we can do the age structure, right? Based on this life table. So this age structure here is based on the raw data. The raw data, the organized data here, we had, let's get here, 5 to 9. 9.9 million women. So it's here, 9.9 million women. And men, we had 10.368 men, 3.68 million men. So I'm just doing the age-sex structure here by sex, men and women. Now let's take the assumption of the stationary theory, the one that Elon Musk used in his tweet. Let's consider that there is no migration. Let's consider that the amount of people being born and dying overall in that country in that year is similar. And let's consider that the age-specific mortality rates is constant over time. So, what are the assumptions here? The assumptions, we have age-specific mortality rates constant over time. So that relates to this column here, age-specific mortality rates constant over time. Let's just get this slide here so you remember, just to mention, just really, this one here. Mortality remains constant, right? Right here, mortality remains constant. Let's say that mortality remains constant for a long period of time. Number of births and deaths equals. Number of births and deaths equals are the same for several generations. Where do we have this here? The number of people being born and being exposed to this chance of dying is here. The number of people dying is here. How many people dying overall? Can you tell me? If I sum this column here, how much do I get? How much? How much? 100,000, right? All these people here died. That's exactly what the life table is doing. Age-specific mortality rate. Let's say that this age-specific mortality rate will continue for several generations. Let's consider that the number of people being born in that country will be always the same as the overall number of people dying. And the last one, no migration. No migration. So no migration, which is not feasible for the US because the US receives a lot of immigrants. Number of births and deaths is not the same. It has not been the same for several generations. And mortality has been fluctuating, has not been so stable over time. Even in 2014, because of the opioid crisis in the US, we already saw declines in life expectancy at birth. And now, because of the pandemic, declines even more. So these three assumptions, they actually it doesn't happen in our actual population because age-specific mortality rates are varying. The number of people being born and dying is not the same. And we do have migration. But just to have an idea, if the US, the number of people being born equal the number of people dying, the age-specific mortality rates remain the same, and there was no migration, how would be the age structure of that population? You just get this column here. You get this column here, and you treat it as the size of your population, because that's the number of person years that people live in the interval. So we get this for women and for men, and I put it here in this other tab. So for example, here, from 5 to 9, 496,000 is exactly this number here, 496,000. That first cell there, I'm adding these two, 0 to 1 and 1 to 4 is here. For males, the same thing. 0 to 1, 1 to 4, I add them here. I'm adding the two cells, and then I get the other ones. And I use this as being my population. And then I calculate the distribution. I get the population of women in each one of the age groups divided by the overall size of the woman population. And the male, I do the same thing. And then I see this. This is the structure of the population. In the case that there is no migration, in the case that the number of people being born and dying in that country will be always the same, number of people dying and being born is the same, and the age-specific mortality rates will remain constant for several years. Then this would be the age-sex structure of the American population. And that's what I mentioned to you before. Demographers say that in this stationary scenario, we would forget our past in the sense that it doesn't matter how it was before, it will approach this distribution in which we have really rectangular distribution here. It might vary from one country to the other, but it kind of forgets our past, okay? But this is the basis to do population projections. But we have to include migration, and we have to update our data on a continuous basis because mortality is varying over time. And number of people being born and dying is not the same, right? But we start with this, but then we go forward. So that's not so easy as multiplying only the number of people being born by the life expectancy at birth to know what's the size of the population is going to be in the future, right? It's not so easy of getting the life table and getting the big LXN to see how the age distribution is going to be, because these assumptions are not true to our actual population. Okay? Cool, any questions? So this was the more technical portion of this chapter. And now we go into a discussion more about the trends and levels of mortality in the world and in the US. So we're just talking a little bit about this short history of mortality in the world. And I use this material from our textbook, from Dudley Poston, but also from this other textbook that I have also been using here in my lectures. So let's just define the health and mortality transition, talk about health and mortality changes over time, talk about lifespan and longevity, which is something that we already mentioned, disease and death over the life cycle, causes of poor health and death, and health and mortality inequalities, right? So whenever you're talking about mortality, we also are talking about morbidity. We have two things here that we are talking at the same time, health and death. When we are talking about health, prevalence of disease in the population, that's related to morbidity. And due to these diseases, people can die. And we can analyze the pattern of mortality, the pattern of death. So what are the diseases that are the most prevalent in the population? I'm doing analysis of morbidity. And or I want to understand the pattern of death. I'm doing an analysis of mortality. And as we discussed in the chapter about theories of demography, specifically about mortality, we have seen some transitions in the prevalence of diseases and the pattern of death over time. And this transition is called an epidemiological transition, as elaborated by Omran. in which there is a shift from prevailing poor health, in other words, really high morbidity, a lot of people sick, and high death rates, high mortality, that were caused primarily from communicable diseases, happening a lot to young people, or to babies. So infant mortality rate was really high. The chance of babies dying before reaching age 1 was really high. And we change into this new pattern of health and mortality in which we have an overall good health and low death rates. And we move from infectious diseases that was the most prevalent before, communicable diseases, into this new stage in which most people are dying due to degenerative diseases, chronic diseases at older ages. So we move now to a good health pattern and low death rates related to infectious diseases, into people live longer, and people live longer, they die because of degenerative diseases and chronic diseases, okay? But of course, there are variations over time. And right now we have the pandemic as an example, right? That's an infectious disease that we get it, communicable disease that we get it, and has been affecting more the older population overall, and varying also by other specific groups of the population. Men be more vulnerable, race ethnicity groups also varying, as we're going to discuss further in this chapter. But what is important here is that we have a transition in terms of morbidity and mortality. From virtually all human history, early death was commonplace. Beginning about 200 years ago, we have been steadily pushing death to older ages, so people living longer. The survival of more people to even older ages is a key contribution to the demographic transition. Most people now survive to advanced ages and die pretty quickly. So all reach really older ages and then die really close to each other. The variability by age and mortality is compressed, leading to an increase in rectangularization of mortality. So people reach these older ages and die really close to each other. And what does it mean, this rectangularization of mortality? It can be shown in a graphical format based on this figure here. So this is data for the US, right? Data for the US, the age-specific, the life expectancy at birth, and the life expectancy for all the other age groups from 1901 to 1910. And then we got better, mortality declined, then life expectancy in all age groups, it increased compared to the previous years. So this one here is from 1951 to 1960. And here we have for 2011. What we see here, because mortality has been declining in all the age groups, the life expectancy in all these age groups starts to increase and starts to get a more rectangular shape. And in this hypothetical example here, this last one, it's an exercise in which we just do in a life table. Let's make everybody survive up to age 100, and then after that, everybody dies. So the life expectancy at birth would be equal 108. So after 100, everybody dies. So that's what we would have in this hypothetical population. This is not true data, right? Oh, sorry, I said that these were life expectancy in each one of the age groups, and that's not that. That's the percentage of people alive. The life expectancy in 1901 to 1910 was 50 years. The life expectancy in 1951 to 1960 was 72 years. And the life expectancy at birth in 2011 was 81 years. So low life expectancy at birth. And if you get this exercise of everybody being alive up to age 100 and then everybody dying, we have this hypothetical example of life expectancy at birth equals to 108. So the vertical axis here is showing the percentage of people alive. Let's say that we have everybody alive here, 100% in each one of these years, and we implement mortality. Since mortality was higher in previous years, people start to die faster, and lower percentage of people is alive in each one of these age groups. So this number here is pretty much saying that only around 60% of the people reach the age of 55, each the age group of 55 to 59, back in 1901 and 1910. And based on data from 2011, in this same age group, 55 to 59, almost like 93% of the people reach that age group. All right, so that's how we read this graph. Is related to the percentage of people alive by age group. And the percentage of people alive by age group, because mortality has been declining, we gain the percentage of people being alive in older age groups. For example, here in 2011, this one here, like around 27% of the people reaching at least at the age group of 90 to 94, okay? And this is much higher than we saw in previous decades. So rectangularization of mortality is exactly that. Mortality gets so low that the shape of people being alive by age group gets close to this hypothetical case of really low mortality in which everybody is reaching age 100. For most of history, life expectancy fluctuated between 20 and 30 years. About 2/3 of babies survive to their first birthday. So 1/3 of babies died before reaching age 1. And about 1/2 were still alive at age 5. And now it's 99% of the children are reaching age 5, right? And it was only 50%, only 1 out of 2, okay? Around 10% of the population of people made it to at least 65 years of age in a pre-modern society, and now it's 90, from 10 to 90%, from 50 to 99%. Female life expectancy at birth is high in more developed countries, as we see in Western Europe, US, Canada, Mexico, also Argentina, Chile, Uruguay, Australia, New Zealand as well. But still we see variations across the world, okay? Health improvements, this is a table that kind of summarizes the overall improvements in health. As we talked in the previous slides, the life expectancy was between 20, life expectancy at birth was between 20 and 30 years in pre-modern societies, and this case here is data for women. In the US and Europe in the late 18th and early 19th century increased to 40. And even with more recent data from around 2015, the lowest sub-Saharan African countries had life expectancy of only 46, while for the world was around 73, Mexico 78. So there is a lot of variation across the world, and Japan 86 by 2015. And this is the overall percentage of people surviving to age 1 in pre-modern societies. Only around 63 to 74% of the children reach age 1. Only around 47 to 61% reach age 5. So that's exactly that 50% that I said in the previous slide. Only 8% reach age 65, 8 to 17% in pre-modern societies, and now around 77%. And because of this mortality really high, causing life expectancy to be so low, how many births would be required to have zero population growth? Births to kind of replace the people that are dying. We would need many more people Now we need, on average, just around 2.1 children per woman to have a zero population growth. So the number of children replace the generation of mothers. Okay? Life expectancy in the Roman area was estimated to have been only 22 years. People who reach adulthood were not too likely to reach a very advanced age, although some people did, but that was not the common thing. The plague hit Europe in the 14th century, having spread west from Asia. An estimated 1/3 of the population of Europe may have perished between 1346 and 1350. And what's interesting is that it appears to be the same disease that we have today, and it's not really well known why it was so fatal past then, but probably because of poor health and few resources to battle the disease, right? Medication and so on. So it's 12:50, it's 12:25 now. This topic here about trends in mortality, I didn't cover it all, right? So I just finished here. The Roman area, Middle Ages. So the topic about the exam that will be this coming Thursday, 2 days from now, so we don't have in-person class, we just go up to live tables, right? So just go up to live tables. I will not ask questions related to short history of mortality in the world. So it will be from what we discussed starting the day after the previous exam until live table. And you can check that specific time point on the lectures on YouTube. Okay, so really study a lot for standardization and live table. That's usually the topics that students have most problems because of those formulas. And have a great exam, and I see you guys 1 week from now on Tuesday.